When you think about traveling 150, 160 miles per hour in a race car, you're probably thinking of something that looks like this. But we're not going to talk about that. We're going to talk about something far more interesting, far more dangerous, and way cooler. Something that looks like this. Or that. How about an old Henry J? 55 Chevy. How about this one? Hello and welcome back to the Rage Racing YouTube channel. Today we're going to talk about one of or possibly the most iconic race car styles in all of motorsports, and that's the 1960s gassers of drag racing. These wild, short wheelbase, lightweight cars of the 1930s, 40s, and eventually 50s and 60s models stood high in the air on straight axle front ends, had engines bursting out of the hood, and had attitude about them unmatched by any other race car. Pictured here is a 1941 Wheelies coupe, which was the car of choice of the Stone, Woods, and Cook team. Junior Thompson and Big John Mazmanian also preferred the 1941 Wheelies. Ohio George Montgomery raced a 1933 Wheelies, as did Jack Merkel. The Kohler brothers ran a 1951 Anglia, Dave Koffel a 1949 Packard, and eventually a 1959 Studebaker. There were also countless Tri-5 Chevys and various models of 1930s to 1940s Fords and Chevys. Could you imagine driving 130, 140, or 150 miles per hour in these wild cars? In 1966, before it was retired, the Stone, Woods, Cook 1941 Wheelies was running 9.5 seconds at nearly 160 miles per hour in AA gas, with a bored and stroked blown Chrysler Hemi stuffed inside of it. Early in the car's career, it ran a blown 425-inch Oldsmobile, then eventually a supercharged 467-inch Olds, before moving to the Chrysler Hemi. But let's back up just a little bit. The gas eliminator class was started in the 1950s, and class rules changed from year to year. At the time, there was no staggered starts, there was no bracket racing, no indexing. It was run what you brung, and the fastest guy to the finish line wins. Cars were put into classes based on their weight versus engine displacement to keep it fair for competitors. The few rules they had at the time was that the cars had to have a stock wheelbase, glass roll-up windows, full interiors, stock bodies, steel fenders, and be complete street legal trim. And they also needed legal license plates and legal registration. Other than that, the options were pretty open for modifications, including engine swaps. So at the start of the class, these were real cars you'd see on the street, either purchased brand new from the dealership, or it could be your mom's grocery getter, it could be a hot rod that you built, it could be a car you bought from the junkyard to turn into a race car, but these were just street machines pretty much. The gas eliminator class had the most variety of any other form of racing. It represented all makes, all models, all years, all types, with pretty much any level of modification from completely bone stock to absolutely wild. Now the real show was the quickest and fastest, which were your AA, double B, and double C supercharged cars. Now this is where the peak of engineering and ingenuity took place to take most advantage of the rules to the extreme to make the fastest car possible. Now as the class progressed, they allowed more and more modifications to these cars, and the racers took advantage of that. So before going into the physics as to why the cars look the way they do, with having straight axle front ends, sitting way up in the air, and using the, unaerodynamic, like 1941 Wheelies, for an example, let's look at the rules of the class to see what we have to work with. The class rules changed year by year, so I just kind of picked what seemed to be a good year to work with. So the rules I'm going to talk about, and it's not a complete list, but the general rules we're going to talk about is from the 1966 NHRA rulebook. Okay, so what I've drawn here in black is a representation of the type of car that would have been very popular and actually very successful in the fastest of the gasser classes. So just to go through some of the rules of the 1966 rulebook, you no longer needed to have legal registration or plates, so you could actually just race a dedicated race car. Didn't have to be a street machine anymore. You could have a maximum engine height measured off the crankshaft center line of 24 inches off the ground. You had to have a minimum wheelbase of 92 inches. That's pretty short, 92 inches. But the wheelbase had to be stock for the vehicle. You couldn't alter your wheelbase. You could set the engine back as much as 10% in the chassis. You could have a maximum of a 4-inch chop off the roof. You did have to run 4 fenders and a rear bumper, although those could be fiberglass now instead of having steel. You had to have a driver's seat and passenger seat, but they could be set back as much as 4 inches. You did have to have full upholstery, although you did not no longer need glass windows. You could run the Lexan windows if you want, but you did have to have a full upholstery. And of course you needed 4-wheel brakes. They divided the cars up in the gas class according to weight versus the cubic inch displacement of your engine, and they would weigh you at the track. So your fastest cars were your double A gas, double B gas, and double C gas cars. So these were your supercharged cars. So the double A, double B, double C, when they double the letters, that means supercharged. So double A gas would be your fastest class. And they were 6.00 to 8.99 pounds per cubic inch of engine displacement. Double B gas was 9.00 to 11.99 pounds per cubic inch. And double C gas was 12.00 and up pounds per cubic inch. And these are your non-supercharged classes. So you have A through F, and they were divided by weight per cubic inch of the engine as well. So A gas was 5.00 to 6.99 pounds per cubic inch. B gas was 7.00 to 8.99 pounds of car weight versus cubic inches of the engine. C gas was 9 to 10.99. D was 11 to 12.99. E was 13.0 to 14.59. And F gas would be 14.6 or above pounds per cubic inch of displacement. The most important rule, of course, was that the cars were required to run on gasoline. No exotic fuels like methanol or nitromethane, just gasoline, which obviously is where the name of the class comes from, gassers. Now, even though the majority of the class would resemble just stock or hot-rodded production cars, it was the fastest cars that set the look, the stance, and the attitude for the whole class. These would be your double A, double C, and double B supercharged cars, and to a little lesser extent, just the regular A and B and C non-supercharged cars. Now, although these cars looked as tough as nails and were a handful to drive down the track, giving the fans in the stands a memorable experience just to watch them, the aesthetics were not why these cars were chosen by the racers and builders. Now, given the rules and the tire, clutch, and suspension technology of the time, it was science that dictated that these old cars and the look of the class developed the way it did. The short wheelbase, lifted high stance turned out to be the way to win races. So let's talk about the science that turned this 1930s to 1940s stock production car into one of the most iconic race cars of all time. This style of car actually defined an entire genre of racing. It's in fact what we think about when we hear the term gasser. A lot of the concepts I am putting in this video I actually got out of this book here, Door Slammers, the Chassis Book by Dave Morgan. The physics we're going to talk about today, that we're going to show in a race car here, is a term called vectors. Now, if you're not familiar, vectors are pretty simple. What a vector does is it shows us graphically the resultant force of two separate forces acting at the same time, but in different directions. So what exactly does it mean to be able to graphically represent the result of two different forces acting on the same object at the same time? It's actually not very hard, and it's going to be more interesting once we apply it to our race car here, but for now I'm going to off to the side, I'm going to show you the basics of how vectors work, and we're going to apply those vectors to our race car. Again, just to get an idea of some of the forces that act on the car as we're going down the track. So I have a tape measure here because scale is very important when we're dealing with vectors. So right now, we are just going to use a simple scale of 1 inch equals 1 pound of force. So with vectors, we're using a length of line to represent the amount of force, and then just an arrow as far as direction. So let's get started. Let's say that we have an object, and the center of gravity on that object is going to be represented by this green dot. So just for the purposes of explanation, we're going to say that this green dot is in the vacuum of space, no other forces acting on it, until we start putting forces on it with our markers and our lines. Let's say that this object with the center of gravity represented by this green dot is now affected by, say, Earth's gravitational field, and this object weighs, we'll say, 8 pounds. So there's going to be 8 pounds of force acting on this object. So we'll take our tape measure and we'll measure off the center of our dot. So 8 inches ends up being right there. And as we said, 1 inch equals 1 pound. So that line represents 8 pounds of force heading in this direction where this arrow is pointing straight down. So this line represents both direction and magnitude by its length. Let's say we push this object at exactly 90 degrees this way. Let's say we push that object with 10 pounds of force. We'll take our tape measure up here and we'll measure out 10 inches, representing 10 pounds of force. There we go. So at the same time, on the one object, we have 2 different forces acting on it. The force of gravity of 8 pounds, pulling straight down, and the force of us pushing on this object this direction at 10 pounds of force, representing by the lengths of the line. So we could also put 8 inches or 10 inches, because our scale is 1 pound equals 1 inch. So what we could do from here is we can connect and complete this rectangle. It's pretty good there. We complete our rectangle. And then we split this rectangle into 2 triangles. So what we're doing is we're taking the center of our imaginary point in space, and we're connecting from that dot diagonally to that dot. And since we both know the magnitude and direction, we can put an arrow here. So what's going to happen is that object that's falling straight down, once we apply a force to it, is going to change direction. That arrow represents that direction, and the length of the line represents the actual magnitude. So I'm going to go through and just do the math on this, just this once, because the math isn't actually the important part. The important part is actually kind of the angle that we're going to be watching with our vectors once we get to our race car. We know from, if you remember from high school, Pythagorean's theorem, that once you have a right angle triangle, if you have the length of 2 sides, you can find the length of the 3rd side by applying Pythagorean's theorem. Say that this is side A, this is side B, and this up here will be side C, the longest side. And that's the side we want to know because we want to know how much force is actually acted on our object. So we know that these lengths are the same, so we know that this is 10 inches, 8 inches, and we don't know how long our diagonal is just yet. So if you remember Pythagorean's theorem, and if you're not familiar with it, it's actually pretty simple. It's just a squared plus b squared equals c squared. So we square a, so 8 times 8 is 64, plus b squared, so 10 times 10 is 100. And of course, you add these together, 64 plus 100 equals 164. We're actually looking for the square root of 164. And the square root of 164 is 12.8. So we know that our line length is going to be 12.8 inches. And since we know that our scale is 1 pound equals 1 inch, the total force combined between gravity and our pushing on our imaginary object, the center of gravity of that object is going to act with 12.8 pounds of force at this direction here. Now, if all of our sides were equal, for example, all of our sides were 10 inches, that would make a square. And if you cut a square in half, we would know that that angle would be 45 degrees for that direction. You can use trigonometry to figure out, because our sides are different, the angle's not exactly 45 degrees, it's going to be a different degree. And that's not what we're going to go into in this video right now, so don't, hit the stop button just yet. Now, vectors work for more than just a 90-degree angle. They actually work for any angle. For example, you could have, let me draw my imaginary dot there. You could have our dot with some force represented by that line going that distance, in that direction. I could have another force represented by that line, that force, that direction. And you just do the same thing to solve like we did before. So we get the angles, come through, and draw your diagonal. And you can figure it out all the same ways you did before. Once you start getting away from the 90-degree angle, though, you have to start working a little bit with more trigonometry to find your right angles and lengths and all that kind of stuff, which would be your sines, cosines, tangents, cotangents, and all that kind of stuff. We're going to take our 1930s to 1940s stock production car, and we're going to turn it into a race car. So we're going to go into a little bit of the advantages of this car to start off with, and then improve on those advantages. So I'll say right off the bat that these cars were, for one thing, very lightweight. They were very small. They had a very short wheelbase as far as where the center of axle to axle is. And they had a fairly high center of gravity compared to the more modern cars of the 1960s. Remember, we're talking about 1960s drag racing here, and 1960s technology. So let's take our car, and we're going to say that the center of gravity for this whole car is going to be represented by this green dot. Right about right there. Hope you can see that. In fact, I'll take that green dot and I'm going to circle it with red to make it stand out a little bit more. Put a little red dot right in the middle. Perfect. We'll say that the center of gravity for this entire car is right about there, which would make sense. The engine and transmission are towards the front of the car. The back of the car is mostly just empty trunk space. You do have the rear axle, which weighs quite a bit, but for the most part, the center of gravity is going to be more towards the front of the car. Like I said, these cars are pretty lightweight. In fact, they were really close to about, let me see this on the camera here, I'll put it up here. They're really close to about 2,500 pounds. And at least for this example, I don't know the exact weight distribution or how much percentage of the weight was front to rear, but we're going to say that, at least for our example here, that the front carried 60% of that weight and the rear carried 40% of that weight. So when we divide it up, what's touching the front tire, or excuse me, what's the amount of weight on the front tire would be 1,500 pounds. And the amount of weight on the rear tire would be 1,000 pounds. So that's the difference between 60% and 40% of our total 2,500 pound car. So right now we're still looking at this two-dimensionally. You can think about it as, of course, there's two front tires, two rear tires. So each rear tire would have 500 pounds of force contacting the ground for a total of 1,000. And each front tire would have about 750 pounds of force pressing down on the ground for combined 1,500 pounds. But right now we're just going to think about this two-dimensionally. So we're just going to say 1,500 pounds in the front, 1,000 pounds in the back, and we're just going to represent that with one tire each at the moment. Now the center of gravity of the car represents the entire weight of the entire car. So there's 2,500 pounds worth of force, or mass, we'll say, 2,500 pounds worth of mass, centered right on our point right there. Now that's an actual point in the car. If you put this car into outer space and you spun it, it would spin and rotate around that axis. That is although not visually being able to see that point, that is a point that actually exists on this car, and that's where the center of gravity is. Everything has some kind of center of gravity, and everything will spin around that center of gravity, with no other forces. For example, if you're out in outer space, you could even have some crazy shape like this, I guess an L. This has a separate center of gravity as well. So let me just kind of block this in so it's a little easier to see. Let's say you got a chunk of steel, chunk of heavy steel that looks just like that. Well, this chunk of steel has center of gravity too, although that center of gravity isn't even going to be on the steel. It's going to be somewhere around there, right? So if you took this chunk of steel and you spun it out in space and just let it free float and spin, it would actually rotate around, probably not really around that point, but you kind of get what I'm talking about here. It would actually probably be a little bit closer to the center here. But the point I'm trying to make is the center of gravity is something that absolutely exists, but it's not a tangible thing we can touch, feel, or even sometimes see. So the center of gravity on this car, we'll say, is right there for now. But that center of gravity represents the entirety of 2,500 pounds worth of force going down. Going straight down. It just happens to be that the weight of 2,500 pounds is divided up between the front tires and rear tires. The way this 2,500 pounds in this car is actually going to react to outside forces is going to be centered around that center of gravity point right there. But for right now, we're going to represent with an arrow of 2,500 pounds pushing straight down in the car right there. This is already starting to look like one of our vectors, doesn't it? Well, let's draw some vectors. Now, before, when I used my tape measure and drew the last vector, I had a scale of 1 inch equals 1 pound. Well, right now we're dealing with a 2,500 pound car. I'm not going to draw a line 2,500 inches long. So we just change the scale. So the scale we're going to use now, I'll write back here. It looks like you can see that on the camera. 1 inch equals 250 pounds. So acting on the center of gravity is the entire weight of the entire car of 2,500 pounds. So 2,500 divided by 250 is 10, so 10 inches. So we're going to draw a line 10 inches down. This represents the amount of weight that center of gravity is going straight down towards the center of the earth. So the front tire is 1,500 pounds, so 1,500 divided by 250 is 6, so we'll draw a line 6 inches long going up from the contact point, so from the ground. So the rear would have a line 4 inches long. So 4 times 250 equals 1,000 pounds. So we'll draw a line 4 inches going up. So put a little dot here, put an arrowhead. There. So those are our static forces right now as the car just sits, say at a starting line or just in your garage or driveway. So the center of gravity is pulling down with the full 2,500 pounds with the force, but it's being supported by 1,500 pounds for the set of front tires and 1,000 pounds for the set of rear tires. So represented by these lines here. Right now we're just working with the rear of the car and the center of gravity and the forces that's going to act on both of those. So let's say we decide to accelerate this car with 500 pounds of force. So as you know, the engine rotates a crankshaft. The crankshaft goes to the transmission. That transmission goes to a rear end. The rear end twists the tire and applies force to the contact surface on the ground, and the tire pushes the car down the road. Right now we're going to say there's 500 pounds of force propelling the car forward. So the way that would look, 500 pounds divided by 250, this line would be 2 inches long. So we'll draw a line 2 inches long and put an arrow like that. Now for every action, there's a equal and opposite reaction. The mass of the car is going to try to resist moving. So it's going to resist with 500 pounds of force. So let's draw 2 inches going backwards. Okay, now you remember how we completed our vectors. So let's draw 2 inches here, and we'll draw 2 inches here. It's going to end up right about there. So the way it works out, once we put all our lines in, center of gravity is going to kind of shift from this point down to this point. See, there's a little bit of an angle there now. And this, the contact patch, the force, the combined forces, end up being at that angle. As we start applying force propelling the car forward. The resultant force of the contact patch and the thrust is tilting towards the front. And the resistant force from the center of gravity is from a static pointing straight down and rotating back. What happens if we add more force? And let's make it 2,000 pounds worth of thrust. So 2,000 divided by 250 is 8 inches. So the tire is going to push forward with 8 inches of force. So that's right about there. Let's draw an arrow. Going forward by 8 inches, and another arrow going backwards. By 8 inches. Kind of see what's happening yet? Let's continue with our vectors and see what's happening. So again, we'll put our dot here. We'll complete our box. And we'll put, so there's for the front center of gravity and complete this box. This box. Okay. So now let's draw in our diagonals. So just kind of eyeballing here. There's the diagonal, the vector, for how the forces, combined forces, are acting on the center of gravity. Just like this diagonal, I'll put an arrow here, and it might be a little hard to see. This diagonal is the vector for the combined forces for thrust on the car. Now let's look at something here. What's happening? I'll use the green marker representing for the center of gravity, and I'll use the red marker for the forces acting on the rear of the car. So as we apply more force, I'm going to use the center of gravity here. As we apply more force, the center of gravity starts to shift back, and the amount of thrust is shifting forward. Notice they're starting to point towards each other, aren't they? What do you think happens when they point right at each other? Well, if you guessed that you get 100% of the weight of the car on the rear tires, then you'd be correct. That is when a wheelie starts to happen. More weight on the tire means more traction. And we saw that with the center of gravity vector pointing more and more towards the back of the car. The more weight you can get on the back of the car, that's the more weight on the contact patch, that's more weight on the tire, and therefore the more traction you have. Now, if you can get the entire weight of the car on just the rear tires, you would have maximum traction. Now let's stop just a minute to talk about the amount of force you could apply to the rear tires that you're trying to hook up to accelerate the car. Well, horsepower back then actually was not in short supply. They had pretty good high horsepower engines. The key was trying to get it to hook up and push the car down the track. So let's say you had an engine, which it'd be easy to have 500 foot-pounds of torque. Hope you can see that. So 500 foot-pounds of torque making it to the transmission. Let's say the transmission had a, say, 2.5 to 1 first gear ratio. So 500 times 2.5, we're already putting out 1,250 foot-pounds of torque to the rear end through the drive shaft. So that's what comes out of the transmission. It is not uncommon for these drag cars at the time to have rear end gear ratios as high as 5-to-1, but right now we'll just say 411. So let's say you got a 411 gear. So we'll take our 1,250 foot-pounds of torque times 4.11, and now we got 5,130, about 138 foot-pounds of torque going down to the rear end, divided in half towards each tire. But we'll just, right now we're just going to say towards the drive wheels, there's 5,138 foot-pounds of torque going to the drive wheels. Well, how much force does that actually make at the ground? Well, that's where we need to find the radius from the center line of the axle to the ground, the radius of the tire. So let's say you had a 28-inch tall tire. The radius is going to be, of course, 14 inches. 1 foot is 12 inches. So 12 divided by 14 is, say, 0.857. Multiply that by our 5,138. Equals 4,403 actual pounds of thrust. So what do we think would help with transferring the weight onto those rear tires as quickly and kind of as violently as possible, so we can get as much traction as soon as possible to accelerate this vehicle down the racetrack? Well, if we looked at our contact patch where the thrust is being applied, of course it's on the ground, so it's very low, which is good. Center of gravity is up here. So actually we're kind of driving under the center of gravity. If you apply a force here and the center of gravity is up here, automatically you're trying to drive under it, which is going to transfer weight to the rear tires. What if we made that center of gravity even higher? Well, what's a couple ways we could do that? Let's look at this. The most obvious thing for me, what if we made the car taller? Let's do that now. There we go. This looks a little better, a little bit more like you'd think about of a gas or race car. I know it's crude, but it gets the point across. So the center of gravity of the car itself is still in the same spot, but since we lifted the suspension, we pushed the ground away pretty much, lifting the car up, and now we have more distance between the contact point and the center of gravity. It would make sense that this would be able to wheelie a little bit easier and get the weight transfer onto the rear tire a little quicker. And we're going to show that with the vectors in just a second. But we're not quite done modifying yet. We still have to do a few more changes to this car. So, for one thing, the engine. The engine is big and it's heavy, and for one thing, it's not big enough since it's not sticking out of the hood. So let's first put an engine in here, and let's put that engine back as far as we can in the chassis. So instead of the engine being like up here, we're going to put the engine right back here, and we're going to make a nice big supercharger coming right back, right to the driver compartment. So we got our blower belt here. The the support ribs on the blower. And of course we got our scoop. And just because it's fun, a couple injector lines, that sort of thing. There we go. So now we did two things. By moving the engine back and building it up, putting more weight up high with the weight of a blower, and you could also lift the engine up in the chassis, getting up as high as you can. We did two things. We changed that center of gravity up and back just a little bit. So let's move our center of gravity. Let's see here. Get the right pen out. We moved our center of gravity, let's say up here and back here. Now the center of gravity is going to be right about there. This is exaggerated, but this is all just to show a point. There's our center of gravity. Up and back from the original location, just from the modifications of the engine being pushed up and back in the car. And then compared to the ground, the center of gravity is even higher just because we lifted the suspension up so high. So now it's starting to look a little bit more like a race car. In fact, I won't be happy with it until we have some headers coming out here. Zoop, zoop. There we go. I know, I'm a terrible artist. There we go. That's much better. Now it looks like a race car. Okay, so we should do our vectors. So moving the center of gravity back changed our weight distribution. So before, we used to be at 60% and 40%, right? Okay. Moving our center of gravity back changed the percentage of weights actually on the tires. All right. Let's just say it changed by even 5%. Just 5% might make a difference, right? So now let's say we are at 55% and 45%. There we go. So 2,500 times 0.55 are 1,500 pounds just by moving the center of gravity back and changing our weight distribution by 5%. We've gone from 1,500 pounds in the front tires to 1,375 pounds. And 2,500 times 0.45. And our rear of the car went from 1,000 pounds to 1,125 pounds. By the rule books, if you remember what I said before, for AA gas, the car had to weigh 6 pounds per cubic inch as a minimum. Now, the engine we put in there, we'll just use the Stone Woods and Cook car as an example. The Stone Woods Cook car was, right there, 467 cubic inches. Is a 467-inch supercharged Hemi at the time. So, at 467 cubic inches, times 6 pounds. Well, the car has to weigh a minimum of 2,800 pounds. Technically 2,802. Just for simplicity's sake, we'll just say 2,800 pounds. So now the weight of our car has gone up by, by 300 pounds, 2,800 pounds. So from 2,500 pounds to 2,800 pounds, just to make the rules for the class. But since we added our great big heavy engine to the front of the car, even though we moved it back in the chassis as much as we could, it still added a lot of weight to the front of the car. We don't want that because that'll mess up our weight distribution. We want to keep our weight distribution, even though we added a big heavy engine in the front of the car. So what do? We add a lot of weight to the back of the car. So as long as we have to add weight to the car to get up to our class minimums, we add weight to the back of the car. So let's put in a great big heavy bumper. And if we have to, we could shove more weight in the back of the car and in the trunk. We can put weight up high, down low, wherever you want to put it. That's kind of the advantage of starting with a lightweight car and having to add weight to get to a minimum class weight break, is you can put the weight wherever you want it. And depending on how the car reacts, you may not want it all the way in the back. You might want it somewhere else. But you can put that weight where it's going to be best for you. So now we put a big heavy engine in the front. So we put a lot of weight in the back to kind of keep our weight distribution where we're happy with it. And right now we'll say 55% in the front, 45% in the rear. That doesn't seem too bad to me. Now we got our car up to weight. We got our big engine. We got our sky-high jacked up suspension. We moved the engine back to get the center of gravity up and back in the car. So what do we need to do? Well, we need to fix our weights on the ground. So these numbers no longer apply since they don't add up to 2,800 pounds. So we'll take 2,800 times 0.55, and that makes 1,540. For the front. And 2,800 times 0.45 is 1,260. There we go. So we managed to keep our same weight distribution percentage, 55 front, 45 rear, but our weights went up, so we got 1,540, and just to check it, plus 1,260 equals 2,800 pounds. So let's start with these vectors again and see where we're at now. And just to see what happens, we're going to keep with that same 2,000 pounds of thrust that I showed before in the last example. Even though the cars could definitely put out way more thrust than that, we're still going to use our 2,000 pounds and see if this car is actually going to do a wheelie simply from thrust. So let's do some vectoring. So 2,800 pounds divided by 250 pounds per inch on our scale makes right about 11.2 inches. We'll just say 11.25 inches straight down. Right there. It's a heavier car, so it's a longer line. So we got 1,260 pounds on the rear tires. So divide that by 250. And we get 5.04, so pretty much right about 5 inches. So 5 inches up. Looks like it's going to end up right about there, right in the middle of our shock. There we go. From our contact patch. All right. So now let's add some thrust just like before, would be the same length. 2,000 divided by 250 for our 1 inch equals 250 pounds is 8 inches. So we got 8 inches back. 8 inches back. 8 inches forward. 8 inches forward. Let's connect those lines. We'll draw our vectors, and we'll see if this thing's going to wheelie or not. So then we connect our dots. Finish off our squares. Okay, so the center of gravity of the car is going to go towards that point there. The thrust is going to go towards that point right there. Well, it's closer to getting 100% of the weight transfer on the rear tires, which may mean doing a wheelie or at least just kind of skating the front end so it's barely touching the ground. Let's look. Again, I'll use the green marker to represent the forces on the center of gravity, red marker for the forces of thrust. So the green marker kicks back to this angle. Red marker kicks for thrust goes to this angle. Oh, so close. If we just went a little bit further, we could have got 100% weight transfer. So what do we need now? Well, let's try more thrust. How do we get more thrust? Well, let's change. Sometimes you can build a bigger engine. You could change the gear ratios in the transmission. You can change the gear ratios in the rear end. There's all sorts of ways to get more thrust. Okay, we got pretty close last time with just 2,000 pounds worth of thrust to deliver the weight, 100% of the weight to the rear tires to get as much traction as possible. But we weren't quite there. Weren't quite there yet. The car's looking pretty beat up after all the drawing and erasing, so hopefully we can get it this time. What did I use in my last example? I said 500 foot-pounds of torque going through an average transmission and an average gear ratio in the rear end would make 4,400 pounds worth of thrust to the rear end. Maybe we'll try that. And that's even a low number. Those cars back then could easily make way more torque than that. They probably had more gear ratio. That's just numbers that I threw out. So in our fictitious example here, let's try 4,400 pounds of thrust. We easily made it that time. Not even close. So let me use the markers because I know it's hard to see. So again, green marker is the center of gravity of the car. The red marker is represents the contact patch, the amount of force being applied. So the green marker hits that angle. The red marker matches and easily passes. So not only are we doing a wheel stand, we're doing a real good wheel stand. All they had to do is touch to get 100% of the weight transfer to the rear tires. We actually went beyond. So I guess the 4,400 pounds of thrust was a bit of an overkill in this example. This is by no means very scientific. I realize that. This is just to show some of the forces that's actually happening in your car. Okay, so everything I showed you on the whiteboard here with all these drawings, what does all that mean? Well, absolutely nothing. Sorry to waste your time. Well, it's not absolutely nothing. So this is just a thought experiment as far as some of the forces that's acting on your car at any one time, or a race car, to get the weight to transfer to the rear tires. So the concepts are absolutely true. And that's also why these cars with their short wheelbases and high stance and high center of gravities was able to transfer the weight quickly to the rear tires and get going down the track as fast as they could. For one thing, I never did get into, once the wheelbases get shorter, it's easier to get the weight transfer, as you can imagine. So these cars, particular cars, are picked because of their short wheelbase. Remember, because of our rules, you can have a minimum of 92 inches of wheelbase, but they had to be stock for the vehicle. You can't change the wheelbase of the vehicle. So these cars were short, they were very light. So to get up to your class weight, you could apply that weight wherever you want. For example, in a situation where you might wheelie too easy, you could actually put more weight up front, or wherever you want it to get you the results you're looking for. You could put that weight high, you could put that weight low. Being able to move the weight of your race car is a big advantage. These were lightweight cars, short wheelbase, and they already had kind of a high center of gravity, so they lended well to the rules of the gasser class and the technology they had at the time as far as clutches and tires and suspension and that sort of thing. So that's why these old 1930s, 1940s old Wheelies and Chevys and all that kind of stuff did well in the class, is because with the rules that were there, the technology that was there, once they were modified, they did the best at getting weight on the rear tires to get maximum traction as quickly as possible to be able to apply force to the ground, or thrust to accelerate down the racetrack. Now, I should say many things I left out. This is just a static drawing. The forces and the vectors involved are absolutely true as far as how all this works, but race cars aren't static. There is suspension, there's tires, there's all sorts of things going on. When you leave the line in first gear, you usually have the engine running, and you usually rev up the engine and dump the clutch. You're storing energy there in the flywheel, and that energy is being transferred once you release the clutch pedal. The suspension is going to sag. The tires are going to squish. As the car rotates, the center of gravity changes as the car rotates. So that's all in motion all at the same time, as well as the ladder bar suspension that they used at the time could be placed to drive the tire farther into the ground, creating a little bit more instant traction. It could it could pull up into the rear end, dropping the car, again shifting how the center of gravity works. There's so many forces and so many things happening in a real race car that you can't possibly explain it with one simple thing like vector. I never even got into the fact that the pinion gear is going to try to climb up the ring gear in the rear end. There's so much going on. But this whole video is mostly just to open up your mind to some of the physics going on in a race car as it's going down the track. So my next video, maybe I will show you how to, in real life, find the actual center of gravity in your car. And I do want to do a video with vectors talking about the differences between the forces applied between a ladder bar suspension and a more current 4-link suspension. So until then, thanks for watching, thanks for tuning in, and keep an eye out. We'll have more videos posted real soon.